The next talk is on the topic SAR for landslide mapping and monitoring. And we are privileged to have with us Dr. Tapas R. scientist SG, NRSC ISRO Hyderabad. Let me now request Bapita, Treasurer IEEE GRSS SBC MIT Manipal, to introduce our speaker for the audience. Bapita, please.
Good morning. With great pride and honor, I introduce the resource person of the next session, Dr. Tapas Martha, Scientist Senior Grade, NRSC ISRO Hyderabad. Dr. Tapas Martha is a geologist by profession. He has done his post-graduation from IIT Dhanbad and PhD from University of Twente, the Netherlands. He has over 22 years of working experience at NRSC ISRO Hyderabad. He specialized in remote sensing and GIS applications in geological studies, including landslide disaster. His major contributions include assessment of Kedarnath landslides, Kerala landslides that took place in 2018, Chamoli rock and glacier avalanche, Kashmir earthquake of 2005, Sikkim earthquake of 2011, and also Nepal earthquake. In recognition of these contributions, he has received Pecora Team Award from International Charter Space and Major Disasters and many awards from ISRO itself. He has nearly 95 research publications to his credit. He has supervised around 17 MTech students and currently guiding 4 PhD scholars. He has visited many countries including Netherlands, Spain, France, Nepal, etc. and also delivered invited talks at several forums. He is currently the Deputy Project Director of ISRO's Disaster Management Support Program and heading Geodynamics and Geohazard activities at NRSC. He is now working on development of new techniques for landslide early warning for the benefit of the society. We are glad to listen from you, sir. Please take over.
Tapas sir, you can start your presentation. Your mic is muted.
Yeah, am I audible now?
Yeah, yes, sir. Yes, sir. Yeah, perfect, sir.
Yeah, it's getting auto muted somehow. I'm not sure how, but
now it is possible.
Okay,
it's okay. It's okay.
Yeah. So you're able to see my slides also?
Now it's not in slideshow mode. Yeah, now it's perfect, sir. You can start, sir.
Okay. Thank you. Yeah. Good morning, participants, and I would like to thank Dr. Samlal and Dr. Silpa for inviting me to this IEEE-GRSS lecture series conducted by Bangalore chapter. And I'm extremely happy to showcase some of the work done at NRSC ISRO in the field of landslide studies. As you can see, my topic is how SAR data, synthetic aperture radar data, is being used for landslide mapping and monitoring at NRSC Hyderabad. To start with, now I am into my second slide, so I hope it is also moving in your Microsoft Teams.
Yes, sir.
Can you confirm? Yeah. Okay. Thank you, Dr. Sita. So let's begin. I mean, what kind of disasters we are facing? So India is number one in the world to say in terms of fatal landslides. There are many countries which are facing landslide disaster. Most of them are in the Southeast Asia and South Asia. Let's say China, Nepal, and Bhutan, and then Indonesia, Pakistan, Sri Lanka. At the same time, in European countries like Italy and Switzerland, Austria, there are many places where landslides occur. And in North America as well as South America, particularly in the Rockies and Andes Mountains, we have lots of landslides. Okay, so but among all the countries, India is number one in the world in terms of landslide disaster. And some of the database which we have compiled at NRSC, around 10,000, more than 10,000 people, they have lost their lives since last 2 decades because of the landslide disaster. This is quite big number. and you know every year the number is increasing because we have climatic extremes in terms of glacial melt in the high altitude Himalayas, in terms of extreme rainfall, short duration but high intensity rainfall in the peninsular India, particularly Kerala, Karnataka, and Maharashtra, particularly in the western Ghat areas. That adds to a lot of landslide in addition to the flood disaster. Okay, so we have to do something by which we can minimize the landslide disaster, something in terms of early warning. I'll tell you the SAR data, some of the slides I will be showing in my subsequent presentation. The SAR data has great potential for landslide early warning, so that we can minimize the loss of life and damage. But how far, because SAR is a new development, but before that optical images were heavily used for landslide mapping. Optical, I mean particularly those in the visible and near infrared region of the EMR, the multispectral image like LIS-4, LIS-3, Cartosat, all are ISRO satellites. There are many international satellites also like Worldview, Pleiades, ComSat. There are many satellites. But the problem is these optical satellites need a source for energy, that is a sun energy, solar energy. And in cloud season, particularly in our monsoon season, where we have a thick cloud cover, we can't get the optical images. So and all the landscapes mostly occur in the cloud season, I mean monsoon season. So how to do with that? Then comes the synthetic aperture radar. It is active remote sensing. That means we are sending signals from a radar, a space-borne radar, and it is hitting the ground, and in the backscatter we are getting recorded at the radar sensor, or received by the radar again. So in that process, we have all weather, particularly in the monsoon season. Also, we can have, even though it's a cloud cover, we can have satellite data within SAR images, and we have day and night, and we can have early morning, late night, anytime we can have the satellite data using SAR. So that adds to monitoring landslide in monsoon season, which was not possible in using optical images. So that's the positive of SAR, but there are certain limitations. I'll be telling you that also. When we come to SAR for landslide, then we have either amplitude data or a phase data. So SAR amplitude change detection, particularly, or radar vegetation change detection, they can potentially identify landslide in tropical region. That means we have bitemporal radar, let's say T1 and T2, and in between T1 and T2 there was a landslide, so we can map that. So that could be amplitude change detection or radar vegetation change detection when we have a polarimetric radar data. Then comes to phase data. Phase data will help you to find the deformation. So at what rate the slope is getting deformed, it is getting displaced. So we can study continuously over a period of 2 to 5 years, that we call as MTI, that is multi-temporal in SAR, and we can find how the kinematics of the slope is changing. So that is how using INSAR we can do. So radar per se towards landslide, we can use both amplitude data as well as the phase data. Now look at, I was telling you, the global cloud fraction and the landslide occurrence. If you look at that place, this bright patches, the bright color is nothing but where we have basically cloud fraction is 1, that is maximum cloud. So you can see in our this part in the Brazil, as well as in this Africa, particularly also in the Mexico and the Caribbean, where we have a lot of areas where we have high or thick cloud is there. Similarly, coming to India, we have in the peninsular India, we have a lot of cloud. In the northern part also, we have, even though not always cloud, but most of the time we have cloud. Same times in the Indonesia also. So if you compare the red dots, which are nothing but the places where the SAR data has been used for landslide studies, and the places where the cloud fraction is quite high, you can see there are a lot of potential still left to study the landslide disaster using SAR data. So previously we don't have much satellite data per se, like RadarSat was there, then ERS, NVSat, then came the Sentinel-1 or 2, then came our ALOS from JAXA, then TerraSAR, and now we have multiple satellites in radar working many private space agencies. ISRO per se, previously they don't have any radar much. Now we have RadarSat 1, RadarSat 1A, and we are going to launch also NISAR with NASA. So these are the new sensors coming up. So this tells you that in future there are a lot of potential to use radar data for landslide studies. Okay, I hope you're able to see my screen.
Yeah, yes, sir. Yes.
Yeah. Okay. So now, before going much into the in the SAR topic, let me tell you briefly about landslide. I'm not sure all the participants how much they're exposed to the landslides. Some of you who are from hilly states or hilly areas, they must have seen on the ground. But to those participants who are not familiar, you can see this is the picture of landslide, how they look on the ground in the hilly area. So this is a big, I mean, this particular size here is almost half kilometer long and roughly a quarter kilometer width. And this is called the top part, where it's called the crown of the landslide. You can see right side, I have given you a sketch where the different morphological aspects of landslides are quite well explained. The top part is crown and the bottom part is called a tip of landslide. The length from tip to crown is called as length of landslide. Okay. So when the crown of landslide means that place from where the material will slide down, and the tip means the place where the material will be deposited. Material in the sense like rock or soil or a mixture of rock and soil, depends on the site condition. Like in Western Ghats, you go to Kerala and Maharashtra, there we have a good lateritic soil. So there we'll mostly find the debris which is coming down. But you go to Himalayas, where mostly hard rocks are exposed, and the landslides are controlled by geological structures like joints and faults. So in that case, that will be mostly rock slide. The main scarp, that means the open area which is exposed after the landslide, that will be quite big. So the top part is called a zone of depletion. That means the place from where the material has slided down. And the bottom part is called as, half of the bottom part is called a zone of accumulation. That is where the material has been deposited. So these are the various features of the landslides, which I can tell you. Okay. That was how the landslide looked on the ground, but now how we map landslide from the space data. So we can see here on the left side, I am showing you a 3D perspective of an area near Palghat in Kerala. That was before the 2018 disaster. And on the right side, you can see the same area after the 2018 disaster, a few days after that. These bright linear patches, I hope you are able to see these bright linear patches. They are basically where the landslides they occur. Okay, these are basically the linear features. They look bright. Very well, you can map it, its size, its location, length, width, etc. using the satellite image. These are the advantages of satellite data when you study landslide disaster. Why? Because they happen in the hilly areas and it's very difficult to climb all places to do our measurements. So whenever we have such cases, then we rely on the satellite remote sensing to get some meaningful results. But now this is with the optical images. So by mapping this kind of landslides, you can see now here how the landslides were distributed in our country. And more or less, we have divided India into 3 provinces. We can see the northern province here, where we have Uttarakhand, Himachal Pradesh, Jammu Kashmir, and Ladakh. And then in the northeast, we have 8 states over here. Your Arunachal Pradesh, Nagaland, Mizoram, Manipur, Tripura, then Meghalaya, Assam, and Sikkim. And then the southern province, where we have Kerala and Maharashtra and Karnataka and Goa. And if you look at the distribution of the landslides, so far we have roughly mapped around 80,000 landslides. This database is published already, and it is available in the Bhuvan portal of NRSC. And you can have a fairly idea how the landslides were distributed in our country, so that you can focus your future studies of the landslide disaster using SAR data, let's say to understand landslide kinematics or to do some landslide early warning. You need to focus in the areas which is already witnessing lots of landslide, and this starters will give you that. So we have a state-wise distribution of different types of landslide, whether it's a event-based landslide, that means the event has occurred after some earthquake or after some rainy season or extreme rainfall, or it could be a total rainy season. That is what you are able to identify. So we have roughly 75 to 80,000 landslides mapped in our country, and this will tell you the intensity of landslide disaster we are facing. Now, coming to the global landslides, you can see on the map we have this black dots. These black dots are nothing but our location of the landslides. Okay, and this color you can see. You can see down below this color here, 1, 2, then 3 to 5, 6 to 10, and the greater than 20. So in China and then Indonesia, the studies of the landslides are done quite well, and similarly in the Nepal and also partly in India. Okay, and this is the study which has been done using the microwave data. This is the paper which you have published in Art Science Reviews. I am one of the co-author to that, and you can read it. It will tell you how the X-band, C-band, and L-band data has been used to study landslide disaster in various parts of the world, and what are the scopes for you if you want to do some further studies. Okay, I hope yesterday my colleague Sasi Kumar must have covered something on the basics of the SAR and how it is different types of data, different types of bands and frequencies. But for sake of completeness, let me just give you an overview of how the SAR data are getting acquired. You know, we have always a side-looking radar. So when this side-looking, it has certain swath, and the swath, the nearest to the satellite is called as near range, and the farthest is called as the far range. And it has certain look angle, that means it's vertical, what is the angle at which the radar is sending the pulses. Okay, and we have certain beam width, like we have you know, in the multispectral data or hyperspectral data, we call as what is the nanometer wise, what is the wavelength interval. And similarly here it is called as beam width, whether it's a 40 megahertz or it is a 25 megahertz. That way it is called as. More the beam width and greater is your resolution. But when the idea why I showed you again here is that you must have seen SAR application in crops, in water bodies. They are all fine, because fine in the sense they are occurring in the flat grounds. But when it comes to landslides, you need to focus on the hilly areas. So what are the issues in the hilly areas? We have three particularly. They are foreshortening, layer, and shadow. So you can see here in this down below right figure, we have the radar shadow. That means certain part on the ridge or the mountain cliff, it is blocking the radar signal. So on the lee side, you have areas which are completely blank. You don't have any information on that. And at the same time, because it's an active signal, active sensor, it is hitting the foothill region and the top part of region in different time interval. So your one face of the slope will appear as if it is tilted towards the satellite sensor. That is called as layover effect, and opposite to that is called as foreshortening effect. So whenever we have a steep mountain ridges, the layover is more important. Whenever you have a little lesser hillocks, then your foreshortening is more prominent. So these are the effects. So what I mean to say here is that if your landslide in the hilly areas is occurring within the radar shadow or within the layover area, it is very difficult to get any detailed information about that landslide disaster. Detailed information in the way like its area, its location, whether it is moving or not, these kind of issues will be always there, which are not there in the optical images. With optical is basically on the top view, so we can ortho-rectify the optical image like list 3 and list 4 or CARTO images, then you don't have these kind of effects. But there you have a cloud cover problem, but here you don't have cloud cover problem. So every technology, I mean to tell you, is that it has its advantages and limitations. You need to use either the two or you combine both to optimize your results. Now, as I said, the radar, we have amplitude. Amplitude is nothing but the intensity of the backscatter response. As you know, the backscatter is particularly controlled by the surface roughness, right? And we have also the soil moisture. So these two parameters, these two physical properties of the target, they control the radar amplitude. Well, unfortunately, in geology and in landslides, unlike our crop and water bodies, we don't have any specific parameters where the geological composition or rock composition or say landslide signatures are controlled by the surface roughness or the soil moisture. That way, to identify, I'm telling, just to identify the target in the radar image as a landslide, the surface roughness and the soil moisture are not the characteristic features, unlike in the optical image where we have a low NDVI or high brightness between two temporal T1 and T2 images is a characteristic feature. So what we need to do here is that the change. So with the single SAR image, if you ask me to identify a landslide, it's very difficult for me. So what I need is basically amplitude image for two SAR images, T1 and T2. Then I will be doing all multi-looking co-registration and the filtering, the specular reduction. So these are the pre-processing I'll be doing, and then if I have the polarimetric SAR data, particularly in the HH, HB, and BBH, then radar vegetation index. They're like NDVI, normalized difference vegetation index. We have a radar vegetation index. There's a certain formula, and you can use the T1 RVI and the T2 RVI. Then you can differentiate that from the amplitude image. Similarly, from the sigma naught. Amplitude is measured in the sigma naught. The sigma naught image, you can do a differencing and you can find out whether the difference image has certain characteristics of landslides in that area. This is all about the amplitude. And at the same time, the unique property of SAR, which is not there in any other case, is the phase information. When the radar sends the signal, they are basically sinusoidal waves. Depending upon the radar frequency whether it's a C band or L band, the wavelengths are fixed. In terms of C band, it is basically 5.6 centimeter. In terms of L band, it is basically 24, nearly 23.5 or 24 centimeter. Okay, and similarly for X band and S band and then P band, etc. So when these sinusoidal waves they reach the target, I'll go to the next slide perhaps. Okay. What I'll do is the phase part I'll be showing in my subsequent slide when I'll talk upon the SAR. Okay. So now let me finish the amplitude part. So what study? Now I'm going to show you some case studies. It is some of the theoretical background I have explained. Now I am now going to tell you some case studies. So the SAR amplitude data processing, what we have done is using Sentinel-1 data. I think many of you may be using it now. It is a public data available. And we have the Sentinel-1 pre-event and the post-event. This is the basic flow chart. I mean, you split the Tufts image, then do radiometry calibration, then you reverse the data, then multi-locate. And after multi-looking, then you do some co-registration, then there will be a speckle filter. And the speckle filter, there could be many, but here we have used the frost filter using 3x3 kernel size. So that will reduce the impact of speckle, because for us which are working on a landslide, and sometimes the landslides could be very big, it could be very small also. So it is very difficult to identify landslides if there are speckle in the image. So we have to reduce the effect of speckle, and then we have the ratio. Basically, this is logarithmic product, as you know, the sigma naught, and so we have to do a ratio between T1 and T2 image that will give us the change in the satellite image as a response to a landslide disaster. Let's look at this case study. Okay. This case study which I'm showing now is a Puttumala landslide in Kerala, which occurred on 8 August 2019. It was a tragic incident, and almost some 12 to 15 people lost their life in that. You can see on the right top, I have displayed one list for optical image, and it started from high hill here, and it again flowed down stroke till 2.2 kilometers. It's a very long landslide, and the upslope part, the slope was very steep, and there were soil mass available, lateritic soil mass, and on that day, particularly on the 8th August, in the evening time, it rained very heavily on that. So that's how the disaster happened. When you coming to the amplitude image, the sigma naught image, here we have a C band BB polarization, Sentinel-1. This is the pre-event image, and this is the post-event image. If you look at the area which I have highlighted the circle, okay, that is where the landslide has occurred. So you can see in the pre-event image, naturally you don't expect any signature of the landslide, but in the post-event image also you don't find the signature very conspicuously coming out. So what to do now? So we have done a change between post and pre. On the right bottom, you can see here the shape of the landslide has come out very well in the radar change image. Okay. And you can compare the shape of the landslide which has come from the radar change image with the LIS4 image. That will tell you how the amplitude data is very useful, particularly to getting landslide information in monsoon time, because optical image will come after a few days, but landslide disaster or any disasters, they are very short-lived, and you need to give your results and outputs to the planners or to the civil defense, to anybody who are working on the ground. If you delay, there is no meaning to that. So if your radar image, even though it's a cloud, is in a cloudy cloud cover, then we can employ the technology to get some information about the landslide location. There could be many more like that in the hilly areas. Some will be missed because of smaller size, but the larger sizes will be definitely picked up. This one again in Pettimudi, Kerala, another landslide here on the 6th August 2020. And if you remember, these are all tea estate workers. Some of you, if you're those from that area, this is in Idukki. I think Idukki district near the Munnar town, and almost 70 tea estate workers, they have lost lives. So how it happened is, again, it's a small landslide on this inside image you can see here. On the top part, it failed, and all the failed material, like a slurry, since there is heavy water available, it is super saturated liquid now, it flowed down slope, and it has buried or damaged, displaced all the huts where the tea estate workers were living. And we got a Tapas R X band here, HS polarization image for this area, and since it was raining heavily, the other images were not available immediately. So based on this data, we could identify what are the source areas particularly. You need to know, because already the rescue team has reached on the ground. They are rescuing people, they are giving all the medical aids, everything, but they don't know at that point of time, is there any further danger on the top part of that? Is there any other slope on the surrounding area is going to fail again? No, this kind of study is required to address those issues. So that's what we have done in this study using Tapas R X band data here. And then another unfortunate this year, in Manipur, we have a big landslide. This landslide happened near Tupul railway station. Tupul is a place where the railway workers, they are constructing, and our army soldiers, they were giving security to them. On the night it happened, and most of them died at the Indian Army soldiers. Very unfortunate it happened. But then why it happened, there's a different story. This area was already prone to landslide disaster, but somehow they're going ahead with construction. There was a old landslide. There was a geological fault on that crown of the landslide. We can see here, this is the crown of the landslide. On the left side, the red color image is the Landsat image. On the right side, whatever you have seen is again our X-band image. It is very high resolution, 1 meter from RISAT to HS polarization image. And you can see the shape of landslide is very clearly demarcated. The texture of the landslide body is very clear compared to the surrounding area. And we have also the landslide, when they come to a narrow valley, they will block the river, and that is what happened here also. The landslide blocked the river, and there was a on the Hyderabad side there is a blocked lake was formed. So this is how we use this X-band data here to give some support to disaster management authorities. But again, it is basically our post-mortem. Okay. This is another case study where we have worked using airborne SAR data. This is a Rat Creek landslide in California in US. And under a joint collaboration with ISRO and NASA, we have been working in that area using our airborne SAR, which has flown in the Gulfstream aircraft of NASA. So this area, what you see here is that there is a National Highway 1A, if I remember correctly. But then after some days, there was a landslide, and you can see in this image that the NH is now damaged. So that means the two areas on the other side are cut off. So this is what we have done using L band and S band. The aircraft was flown on 2019 before the landslide disaster, and then again in 2021 after the landslide disaster. So here what you see is basically a RGB composite of HH, HB, and BB. And down below, the spectral plot shows the L band post landslide and pre landslide, the sigma naught values. Okay. So on this section, from crown to tip, if you can see the profile, there is a significant change in the post disaster post landslide response. I'm not sure how it happened, because I have already told you, unlike optical images, the surface roughness may increase a bit after the landslide because the boulders and the soil mass will be lying on the main body of landslide, but the surface roughness is also high before the landslide also. So, but you know, radar response is a complex feature. You never know how the backscatters for a particular pixel element are summed up and recorded, but sometimes we get a difference in the backscatter response, and that is what we could find here. Even further, the NS, the national highway is quite clear in the pre-event, but it is not clear in the post-event. So these are the contexts which also helps us to identify whether the landslide has damaged certain things, and that can be proxy to certain landslide in that location. This is what in L band, and similarly in the S band also. So in the S band also you could see that we also found certain signature of the landslide in the Rat Creek area. But one thing I would like to tell you is that your look direction, which is particularly across the flight direction, it is very important. If it is coming, if you remember my previous slides, if it's coming in your foreshortening area or layover area or radar shadow, so whatever good quality data is there, you can do it anything for any meaningful use. Okay, now coming to the phase. So far I have been telling you about the amplitude information. One thing which I have not covered, but I'll tell you now, is that the coherence change. Similar to the amplitude change, that is the sigma naught change, you can have also coherence change. That means when you take a two time series image, and in between there is a landslide, the two images will not be coherent. Okay, the two images will not be coherent. So loss of coherence, which will be quite high, indicates indirectly that could be a presence of a major land cover change. And if you have all the context in picture, like high slope condition, hilly area, then you can attribute that change to a landslide disaster. There are a few studies, but due to lack of time, I couldn't include some slides. But I have some slides, but somehow I couldn't get time to include them. So coherence change is another thing where you can use satellite SAR data for landslide mapping. Now let's come to MT in SAR. So this is basically what I am going to tell you now is this landslide monitoring. Okay, that means over a period of unlike amplitude, whether you have a T1 and T2, and here here in MT in SAR we have TN. We have hundreds of or a series of microwave satellite data covering a period of 2 to 5 years or anything, and then you do an interferometric SAR. You are able to do interferometric SAR because you have the phase data, phase information available with us, like Sentinel-1. It gives you the SLC product, it gives you both phase data as well as the intensity data. But the RISAT-1 and the RISAT-1A, they are not particularly phase data, which ISRO has launched. There are RISAT-1A, they're mostly used for agriculture, disaster purpose. RISAT-1A has certain opportunistic data planning, wherein few selected modes they will cover interferometric, but that is not applicable to you because it's not available to you also. It is to some specific users like us who we want to test and do some research to further improve our future missions. Okay, so now when you come to MT in SAR, the principle is that when you have one satellite which is hitting the target at T1, and the same satellite coming to the same orbit and hitting the target at T2, but in between what happened is that there is some subsidence happen, which is basically DH or delta H subsidence. That means the H will be the loss of height, and the loss of height means when the T1 and T2, when you do a phase change, that means you generate an interferogram. So when you interfere the T1 image and T2 image, and you generate an interferogram, which is nothing but the phase change. So the interferogram subsequently has to be unwrapped, and number of the change of phase you can find out, and you can attribute that to the displacement. How you are able to tell displacement? Because here your wavelength is 5.6 centimeter. Let's take case of C band. So the wavelength is 5.6 centimeter. So anything half of that, lambda by 2, and it is changing between T1 and T2, you can very well find the fringe out of that after the interfering the T1 and T2 image. So phase difference is nothing but the T1 and T2 phase difference. It consists of certain other parameters also. One thing is the change in the elevation. Okay, that's many reasons. Like it could be due to landslide, it could be due to some underground water removal, or it could be due to some earthquake. There could be many things, but you need to correlate why this change in elevation has happened. And there could be a contribution from the atmosphere, particularly the ionosphere, which tend to change the interference pattern, and could be due to some other parameters which are not completely understood. But some of them, since you have a good baseline between the two acquisitions, you can nullify some of the parameters, or you can assume that as very minimal, and the main contribution is particularly from the difference in altitude. But if you have some higher models also, you can compensate the noise. That means the system noise, the radar noise, the atmospheric noise, and any other parameters. You can compensate for that also. Certain models are available. So by removing effects of the phase difference between due to all the parameters, the final result you can attribute because it is a slope deformation or any other deformation. Now that's one. Now coming to applying that to a landslide. So let us look at these three diagrams on the top. There is called a rotational landslide, translational landslide, and a complex landslide. So in the rotational landslide, what happens if you look at the A dash cross section over here? Let me tell you. I hope you are able to see the slide and the area where I am highlighting my cursor. Are you able to see?
Yes.
Yeah. Okay. Yeah. Okay. That's good. So if you look at this area, the dashed line is particularly the surface before the landslide has happened, right? And this solid line is the surface after the landslide has happened. Okay. So whatever happened between T1 and T2, this particular place has slided down. Okay, so this kind of curvy linear plane of rupture will happen in case of rotational slide. So if you can see on the top, you can say that this has been back tilted. Okay, and in the similar way, in the translational slide, you can see that there is no back tilting. So why I'm telling you this, that when you measure the line of sight displacement, that means radar is looking in the side manner, and along the line of sight, whatever displacement happen, you are going to measure that only, not vertical or not horizontal. Subsequently, you can reserve them to vertical and horizontal. But whatever the deformation, side deformation. But the line of sight deformation could be of two types. It could be a positive, it has moved towards a landslide, the target has come upward. It's negative, it has come downward. But sometimes what happens when you look at the hill, you say that landslide, because of a gravitational failure, it has come down. That means the distance has increased. So it has to be negative. But it doesn't happen like that. Why does it happen? Because you need to understand the morphology of the failure of the landslide. If that is the case of a rotational landslide, then certain feature will go towards radar. That means positive displacement. Like any point target over here, right? Over here, it will go slightly upward. It will back tilt. Similarly, in complex landslides, some features will be showing positive displacement. Some features, some parts of the landslide will be showing the negative displacement. So you may be confused. It may be saying that it's a wrong result, but it's not a wrong result. It's a correct result. It is possible that within the landslide body, you have both positive and negative if you understand type of failure. So that's why you need to do some kind of a geological investigation along with the SAR data processing. And when you see down below, you have the synthetic interferogram, the change of phase. So the red color is plus pi, and this orange color or the pink color is minus pi. So how the radar interferograms will come in case of rotational landslide, in case of translational landslide, in case of complex landslide, it has been well studied. So you understand now, it is not simple that you just find a deformation, but using the deformation pattern, you are able to tell also the type of landslide. So you can ask me, what do I need with the type of landslide? It's very much required. When you have a landslide and you want to do some civil engineering or structural work in that area, the practices, the methods will vary from one landslide to other landslides. So to understand that, if you can get this type of landslide that is rotational or translational using SAR interferometry, then it is very useful. Okay, now let's go to the actual thing what SAR interferometry can give. This is a very good results what SAR can give, and to my knowledge, to my belief, no other satellite data can give, or no other ground data can give for a large area. Okay, when I have said already, when you are doing a SAR remote sensing, we are not focusing on a small area like behind my house, behind that college, like that. What I'm interested in is entire country or entire state. The remote sensing is used for large area, for inaccessible areas. If a local area, you can very well visit that area, do some study, collect some soil sample, you are happy with that, then that is done. But when the remote sensing you are coming, you should work on the larger area, regional area. Okay. Now let us go to what exactly it can help us. If you look at the life cycle of a landslide, let us focus on this figure. On the y-axis, we have a displacement, and on the x-axis, we have a time, right? And it initiates the slope, how it deform is basically some crack will be formed because the shear stress is quite high in comparison to the shear strength of that rock. It can no longer take the load. It has to slide down because of a steep slope, or because of something happened on the toe part. You cut the road, okay, the toe guard destabilizes, or you disturb the angle of friction, something. So then there will be initiation of the failure. The landslide, the larger landslides which are catastrophic, which do a lot of damage, they don't work over, they don't happen overnight. The smaller landslide, like soil creep, like there's a rain yesterday, tomorrow you'll see a lot of landslides, the smaller ones. But the larger ones, it will take some time to occur. And the initial stage is called as the primary stage. That means the cracks will open up, and subsequently after few months or a few years, you will see the steady state of displacement. Okay, and then after some time, when it comes to tertiary stage, this is very important now. Look, when the tertiary stage, the rate of displacement increases exponentially. That means the acceleration is quite high. So when this stage has come, so first of all, what we need to do? We need to continuously monitor the displacement over a period of time. So we have a time series radar. That means Sentinel-1 we have there. It is there from 2015 onwards till today. Okay, so we have the data. Now we should understand by plotting the displacement, what is the curve pattern. If it is increasing exponentially, that means tertiary stage has reached. So can we do something now? In the tertiary stage, it is going to fail. But then when it is going to fail, that is nothing but called as early warning. So when you can tell it is going to fail, but it's exponentially increasing. So we don't know when it will fail. So what we do is a method which was developed by is very popular. It's called the inverse velocity method, which is called as the Fukushima technique. So in the Fukushima technique, what we do, the displacement, from the displacement we can find the velocity, and we can simply inverse the velocity, right? And you can see down figure, the right side is the displacement, and the left side y-axis is basically inverse velocity. When you inverse it, it is going to meet time axis at a certain point, and that point is nothing but the time of failure. So when you monitor and you understand the pattern and it is coming to the tertiary stage, and then you can extrapolate the inverse velocity using Fukushima technique, and you can find out it is going to fail so and so date. Okay, so having said that, let's see what we have done. Now we have done and applied the study on 2 case studies. One is in northern India, particularly Himachal Pradesh, where we have a slide called Kotropy, okay, on the date, I think it was on 13 October 2017. 13 August, sorry, 13 August. So for Kotropy, what we did, we took 42 SLC images of Sentinel-1 and till 12th August. That means 1 day prior to failure, to understand, to find out how was the kinematics of that slope. And similarly, one more case study in Kikruma in Nagaland, also we have processed to find out what is the slope failure pattern in that area. And these dots, the color dots, whatever you are seeing, they are particularly the measurement points. When you do a empty insert, I think I forgot to tell you, when you do a empty insert, there are basically 2 techniques. One is called as PS insert, other is called as SBAS insert. PS insert is nothing but persistent scatter interferometry. Persistence means there are large, you can say, rock exposures or some permanent features or some small house in that. It is persistently scattering its signal back to the satellite in this total time period. But this kind of persistent scatters are very less. So to overcome that, there is another technique called as a small baseline scatterometry. So SBAS. In that, there are persistent scatterer as well as distributed scatterer. So both the scatterer will be there, and it will give you the deformation time series of the ground. If you have a vegetation cover, then this technology will not help. Why? Because you will have a loss of coherence. You need a good scatterer, and as you are going towards L band, I will suggest if you are attempting interferometry or MTI, you go for L band. But unfortunately, there is no L band data, and ALAS pulsar are very costly. But now we have this ISRO NASA mission which is coming up, and it is going to be launched sometime in January 2024, and it will give you L band data freely every if I'm not wrong, every 12 days, like that. It will give you freely the L band satellite data. So then you can do this kind of multi-temporal interferometry using L band, because L band, what happens, you have a larger penetration within the canopy. That means below the canopy there will be some scatterers which will be getting detected in the SAR, the return signal of SAR, and then you can assume that could be a rock mass below the tree mass, so that could be moving, and that is how we can have a more number of scatterer. This kind of color points will be more in this particular landslide. Now, if you look at this Kikruma case study, what we have done, this paper has been already published in the remote sensing of environment. So you can refer that if you want to have more details about that, what are the techniques we have applied. So in the Kikruma case study, you can see here that the acceleration, what we call as an onset of acceleration, it started 60 days prior to the failure. Okay, and in case of Kotropy, the onset of acceleration has started 24 days prior to the failure. So this is what we have done, 0 to 500, that means the days number. We have 42 SLC pairs of Sentinel-1 we have processed in Kikruma, and similarly also in Kotropy, and entire time series deformation we could record it. This is the very beauty, I would say, of SAR data. That means a SAR sensor which is moving on an altitude of 800 kilometer above, but precisely giving you the deformation in the order of millimeter. Sometimes, no, we fail also in our ground-based measurements. And forget, we can't identify in the naked eye also, but a satellite INSAR will help you to do that. That's something which is a remarkable achievement, I would say, which will now helpful for landslide disaster studies. So when you apply inverse velocity method, that is called as Fukushima method. So what you have done now, you measure the velocity and then you have inversed it, and then you put a straight line and you find out on what time it is cutting the x-axis. Okay. Similarly, we have done for Kikruma and Kotropy. And other than the inverse velocity method, there is another method called as modified inverse velocity method. So this mathematical computation is this one. So modified inverse velocity method, V and V0, it will give you also TF, the time of failure. Okay, so if you look at the modified inverse velocity method, Kikruma and Kotropy, we have, I think, this result. Yes, you can have these results. In the inverse velocity method, the prediction of failure was on 26 July 2018. And in modified inverse velocity method, it was on 2nd August, but actual failure was on 29 July. That means both the methods has given us a window of failure. These are complex natural phenomena. Okay, so we can't be that sure that it is going to fail and so on, so date and so on, so time. Instead of that, we'll tell that this is the window of failure between this date to that date. Using these two techniques, we can tell that within this window of failure, there is going to a landslide is happening. Look out for that. Watch for that. Similarly, in the second case study, Kotropy has predicted by INV inverse velocity method 13 August and the modified inverse velocity method on 14th August, and the actual day of failure was on the 13th August. That means there was a 1 day window of failure. So this, I would say, is a safe prediction. But this, we have done a back analysis, not actual analysis. Now we are going to do this. We are going to employ this methodology to do a landslide early warning with addition of few more methods for landslide early warning in our country. But this technology using SAR has given us a tremendous results, by which I can at least tell now, based on the landslide kinematics from the MTI, that this and this date, between this and this date, it is going to fail. Okay, so I suggest participants to look in this direction if you are interested to work on the SAR interferometry or MTI on landslide monitoring and landslide early warning. Now, this is just animation of what I have said now. You can see in Kotropy, we have the stable, basically, I was telling you, that means the secondary stage where there are minor displacement or there is no displacement. And here on this day, we have now 80 millimeter of rainfall on 10 September 2016. And you can see once there's a rainfall, there the acceleration will start. If it is a slow moving landslide creep and it has come to certain stage, that means the stress has increased now, so it is now going to fail in a vigorously. So this trigger came from this rainfall on 2016. So now rainfall and the measurement of deformation you are combining. That's going to be very interesting. Now you see this, once it fails, then it will slide, and it has slided almost 40 centimeter in 1 year, but it has not reached to the tertiary stage. And this rainfall again on 2017, somewhere in the July, last week of July, there is an onset of rapid movement by 23 millimeter, and the landslide happened on this date, on the 13th August. and this is how we can see in the optical image. This is before landslide and this is after landslide. So this is what we have done using C-band interferometry or MTI for phototrophy and pictorial landslide. A back analysis, we found out how we could do it, how we could measure the window failure, what are the techniques useful. This background work has been done, which will be working further towards landslide early warning. One good thing is already I have told you that now we have a NISAR mission which is coming up, and we have a dedicated mode in the Western Ghats. So the Kerala, Karnataka, and Maharashtra, Goa, these areas where the high intensity rainfall that trigger lots of landslide, we have kept one dedicated mode for high resolution L-band and S-band data with 40 to 45 megahertz beamwidth, and there will be 10 to 30 cycles observation each year. Okay, and these observations are planned sometime in April to July. And this is going to be very useful for free data in L-band. Currently, there is no free data in the L-band. So with this, now I would say this is how the NISAR mission is now going to help us in future. Currently, we are using C-band, then the L-band, and there are many new missions coming, particularly by the private players. So we are going to see some good results as far as landslide monitoring and early warning is concerned. So with this, I'll stop here. Thank you very much.
Thank you, sir. Is there any questions from participant sides? Any questions from the participants? Yeah, I think there is no questions from the participant. Thank you, sir, so
Hello.
much. Hello. Yeah. Yes.
Ma'am, I'm Hitaishi from NIT-MAHE.
Yes, sir. If you have question, you can raise, sir.
Yeah.
Please. Yeah.
Tapas sir.
Yeah, please. Yeah.
Sir, you mentioned that the landslide inventory has been made from the NRSC in the Bhuvan portal.
Yes.
Sir, actually, I'm doing a project under like early warning system for landslides using like the rainfall data, fixing the thresholds and all. So that's why, like, can we get the inventory based on like the date of occurrence of landslides?
No, unfortunately, no. Why? Because whatever the inventory we got, it has other parameters, but time tagging is not there. Time stamping is very difficult. Time stamping is only possible when you collect the inventory on the ground. Some activities we have taken up recently, which will help us rather to have a time stamping of the event. But the one which I have shown in the Bhuvan portal, they don't have time stamping. So may not be directly useful to you for rainfall intensity threshold, which is done for everyone.
So how can I get the data like for the time stamping of the landslides, sir? Should we do it manually using the satellite images?
See, satellite
Like
image, what
as far
happened?
as
No?
my knowledge, the GSI reports have some of the landslides information. But
Yeah.
regarding the satellite images, like satellite inventory, how can we do it, sir?
No,
Should we do it manually?
what happened? Yeah, you can do it, no doubt. No, you can do it. Let's say you have a high frequency satellite data source, which unfortunately we don't have at ISRO, but there are very private companies. They are providing data every 2 hours, every every day or like that. So you can subscribe to that, and you can focus on your area of interest, and you can go collect data. So that is one way you can collect the
in all the things
time
it's the
stamping
same.
information.
Like
But the
most of the things what we learn in theory, when we go to the practicals, maybe it's just the
Attendees, some of your microphones are on. Can you please? Yeah.
Yeah, please. Somebody was having a question.
Sorry, continue. Yeah.
Yeah. So the time stamping part is like when you have a high frequency satellite image. So you can map the locations where it has occurred, and you know the time of the image. That means you know the time of occurrence. So that is one way to do it, the time stamping. If you want to do other way, you have to go on some crowdsourcing, or you have to go to the field. Then you can find out the location of the landslide, and you understand the date of event. But then when you are going to the field, you have certain advantages, like you know the location and area. But there are many landslides which will be missed. You don't know whether they were happening or not. So that's what I said always. You have to take both advantages of both part of field as well as for remote sensing, if you are developing some kind of early warning for your area of interest.
Hello.
Okay, sir. Thank you, sir.
Hello.
Yes.
Am I audible? Thank you for the wonderful
Yes,
presentation,
please.
sir. Yes. Sir, my question is very simple. What are the parameters need to be considered while ground truthing? Or what are the essential parameters that need to be considered, particularly for landslide kind of research study?
Okay. Look, ground truthing, what we call is landslide inventory. And the parameters, Geological Survey of India, they have some 42 parameters, like rock type, the soil type, the length, width, type of landslide, cause of landslides. These are the parameters you need to. We have also ISRO also. We have the mobile app which is available in the public domain. You can download that, and we have 20 parameters in that. So when you collect using mobile app, your geotagging is done, photos were taken, everything is done. You need to just some drop down in the mobile app. You need to only select if you have some minor information about the landslide, and then you need to further process it for landslide susceptibility, landslide wall warning, or whatever you want to do. But the basic information will be either 20 or 42. Which one is suitable to you based on your understanding, so you can collect the information.
Okay, thank you so much, sir.
Nagaraj sir, I think you're having one question.
Yes, ma'am. Yes, ma'am. Good morning, sir. Am I audible?
Yes, sir.
Okay.
Yes, please.
Sir, as of now, I am working on change detection of water bodies, sir. But I am new for this SAR image data analysis. But I worked in optical images. For example, list 3 images from Bhuvan portal. So how far this SAR data is used for water body mapping, as well as which band is useful for this water change detection analysis, sir?
Okay, that's a very good question, and answer is very simple. The maximum utilization of SAR data is in water bodies. That means water spread, flood, etc. So which one of you is your interest? Is it flood time or like normal mapping the lakes and ponds, etc.? Which one is of your interest?
Normal mapping, sir.
Okay, so let's say in Tamil Nadu, you can say there are a lot of tank irrigation, right? So if you want to map those tanks, then SAR data is very useful, I would say. Why? Because you don't have a problem of cloud cover, number one. Then the water body is basically a specular reflector. Okay, so your sigma naught values are very low. So you can easily classify the SAR data for water bodies. There is no band concept in SAR data. You have to think of the polarization. Either you take HH or HB, there will not be much difference. as long as it is a still water. Okay, if there is a moving water or it is a large water body where there is a wind effect, there will be minor change. But otherwise, you will have wonderful results from SAR data. You focus on HS or HV, any data, it will give you wonderful results.
Okay. As of now, any publicly available data set, that is SAR data set, available in board portal, sir?
Yes. We have this Sentinel-1 data, which is available in the public domain, free downloadable. You can download from the Copernicus side, or you can download from Bunidhi also, NRSC Bunidhi, where you download other data. Similarly, you have Sentinel-1 data available also. And there are other data which are available on sale purpose, like NovaSAR, RISAT. All data sets are also available. You can download it. Data set also. Sorry, you can purchase it.
Okay. It is available in commercial or purchasing?
The Sentinel-1 is free. RadarSat and ALAS and RISAT and NovaSAR, they are commercial. And there are many more also. I mean, you can just, a lot of private companies now, they have satellites, constellations, and they're giving you satellite.
Thank you. Thank you so much, sir. Thank you.
Yeah. Yes. Any other questions?
From the,
I'll be happy to answer. Yeah. Dr. Silpa, participants are mostly, students or working professionals?
Actually, we have a wide variety of participants. We have from graduate students, master's students, PhD scholars, then faculty members are there, industrialists are there. We got a total of 288 registrations, and maybe yesterday some 100 plus was attending. Today it was a bit less, but still it is an active group of participants, what I felt like.
Sir, one last question, sir.
Yeah, one question. Yeah.
Yes, please.
Sir, you said about water mapping. What about water quality mapping, sir? Is it possible, sir?
No, it's not possible.
Okay, sir. Thank you.
It's not possible. Yeah.
Sorry, sir. May I know the reason, sir? Sorry.
See, the water quality, you mean to know the pollutants in that, particularly you're targeting the chemical composition. So what SAR data is giving you is a physical property, not chemical property. Okay. So that way you cannot do the,
Thank you, sir.
Yeah.
I think we have one more query from 8 Square Engineers.
Hello, sir. I just want to know if there are any slow-moving landslides that you're monitoring. For example, the Western Ghats.
Okay.
Just want to know if that's something you guys monitor.
Western Ghats, we started, but not much because we have only C-band. C-band, since there's a forest area in the Western Ghats, the persistent scatterers are not available. So we are relying on L-band. So some L-band data we got, and some more will be coming when the NISAR will be launched. But right now, we don't have much sites in the Western Ghats. There was a proposal from Manipal Institute to use ground-based INSAR. I remember Dr. Sweta Vincent, I think she was quite interested in developing a ground-based INSAR. It's quite innovative and something that sort of will be very useful. And some of the things which I have shown also has been developed by some of my students. They have been working like the amplitude change and other things also. But right now, no active monitoring we are doing. In future, we'll be doing it.
Thank you, sir.
Yeah.
Any more questions? Yeah, Dev Dinesh.
Good afternoon, sir. I'm Dev Dinesh from IIRS Dehradun. I am working on soil moisture. So, what is your recommendation so that I can do something innovative in that field?
Yeah, I mean, once you're in IRS, you must have been interacting with Dr. Chatterjee and Dr. Sasi Kumar, Praveen Thakur. So they will be telling you what
Shashi is my
do. Okay, so then, okay, anyway, since you have asked the question for benefit of other participants, I'll tell you that soil moisture is one thing which also we are working, how the soil moisture is built up, and the remote sensing based soil moisture is something a direct measurement. Another thing is the model based soil moisture. The variation in the model based soil moisture is not much. That can be used for early warning. But if you have something you can do on the soil moisture, very high resolution soil moisture, like 500 meter or more than that. There are some people who they claim also soil moisture from remote sensing or SAR remote sensing, even 10 meter, 20 meter they can give, but I think that's not possible. So this kind of thing, if you can do and do soil moisture variation like rainfall variation we are studying, but how it is a runoff or it is soil moisture, that matters. That we don't know actually. When you are doing rainfall, it can flow down or it can flow ground also. So that we don't know. But if you can find out soil moisture, and it is very well studied how to measure soil moistures, then that will be useful for remote sensing. Certainly, you can do it.
Thank you, sir.
Yeah.
Sir.
Yes, please.
Sir, for flat area mapping, which band is more useful?
You mean which polarization? Oh, I mean the band, whatever you call.
Yes, sir.
Yeah, that is something which is basically in optical, but here it is called as polarization. So HH band or HP band. I think HH or both. I mean, here we use both. We have a separate group. They use both, depending upon the water condition, the water area spread. Some way HH will be used, some way HV also will be useful. But polarization wise, there is no standardization. Some cases one polarization or cross polarization, the other case another one. So there is, I cannot say like mineral prospecting or kind of a thermal data you use like we do in optical thermal band. Here I cannot just recommend like that way. It depends upon case by case.
Okay, sir. Thank you.
Yeah.
I think there are no more questions now. Hope we can wind up this one. So really, it was really informative and insightful talk, and I'm sure many participants who joined with us today are working in the similar domain and will be highly benefited by your talk. Thank you once again, sir, for your time and accepting our invitation to be with us today. And with your permission, hope I can share your mail ID with the participants.
Yeah, sure. I mean, I'll love to get some feedback and questions from the participants. Yeah, definitely.
Sure, sir. We'll do it. And we are hopeful to collaborate with you in similar events in future as well.
Yeah, sure.
Yeah. Thank you so much, sir. I'll get back to you, sir.
Thank you,
sir. Shyamlal sir is it? Yeah.
Thank you very much.
It was thank you, Shyamlal sir. Thank you.
An informative session.
Thank you. Thank you. Thank you.